What if the next big breakthrough in artificial intelligence isn't just about making models bigger, but making them think differently, perhaps, a bit more like us? Imagine an AI that doesn't just mimic language, but actually reasons, with both that fast, intuitive insight and deep, deliberate thought. Today, we're taking a deep dive into something really quite groundbreaking, the Hierarchical Reasoning Model, or HRM. This is a new AI architecture from Sapient Intelligence. Now, while large language models, the ones you hear constantly talked about, are amazing at generating text, right? They seem incredible, but they often stumble when it comes to really complex multi-step reasoning. They tend to rely on a technique called chain of thought, which, well, as we'll find out, has some pretty significant limitations. So our mission today is to unpack what makes HRM different, how it draws inspiration from, believe it or not, the human brain, and the really surprising ways it's managing to outperform much larger AIs on some extremely tough reasoning puzzles. Get ready to have your understanding of AI's potential and maybe even your own thinking expanded a little. Okay, so let's unpack this a bit more. We hear so much buzz about these LLMs, their incredible capabilities. But when it gets down to genuine, deliberate reasoning, there always seems to be this but. Can you elaborate on why these massive models still face fundamental limitations in, well, deep thinking?
Yeah, you've really hit on a crucial point there. Current large language models mostly use this chain of thought or COTI prompting for reasoning tasks. And, while COTI does help by making the reasoning steps explicit, writing them out sequentially, it's often described as a crutch, not a satisfactory solution. Think about it.
A crutch. How so?
Well, imagine trying to solve a really complex logic puzzle by writing down every single tiny step perfectly in order without ever being able to just, rethink or backtrack easily. It's inherently brittle. One little misstep, even just getting the order slightly wrong, can completely derail the whole process.
Oh, okay. So it's fragile.
Exactly. And it's also very data hungry. It needs a huge amount of specific training data just to learn these thought chains.
Hmm.
Plus, for really complex problems, it ends up generating a massive number of tokens, basically, and that translates to slow response times and, frankly, high computational costs.
So it's less about real internal reasoning and more like this elaborate step-by-step recitation that can easily break down. That definitely sounds inefficient.
Precisely. And there's a more fundamental issue, too. Standard transformers, which are the core architecture for most of these LLMs, they have what's called a fixed computational depth. This means they work within a set number of processing layers. That limits their ability to do complex algorithmic reasoning or deliberate planning purely end-to-end.
Right.
They aren't really Turing-complete in their basic form. A Turing-complete system can theoretically simulate any computation given enough resources. Standard transformers are more like incredibly powerful, specialized calculators, great at specific tasks, but not designed for that kind of open-ended, iterative problem solving. Just making them bigger doesn't always fix this. For really hard, multi-step problems, their performance often, well, it stays far from perfect.
That's a really clear distinction. So if current AI hits this kind of wall with deep reasoning, where do researchers look for new blueprints? The human brain, naturally. How did our own biological wetware, as they say, inspire the design of HRM?
Yeah, what's truly fascinating here is how the human brain offers such a compelling model. It organizes computation hierarchically. You have different parts of the cortex operating at different speeds, different timescales. Think of it like the slow, higher-level areas, maybe your prefrontal cortex, guiding the big picture, the abstract planning, deciding the strategy. Then you have faster, lower-level circuits executing the detailed subordinate processing, like catching a ball or recognizing a shape instantly. HRM mirrors this directly with two interdependent recurrent modules.
Two modules.
Yes, it has a high-level H module. This one's responsible for the slow, abstract planning, like our deliberate thinking. And then there's a low-level L module handling the rapid, detailed computations, more like our intuition or quick reactions. And the key is that these two are tightly coupled. They interact constantly in a very specific, dynamic way.
Okay, so it's almost like having a master strategist figuring out the overall plan, while a quick-thinking tactical unit is executing rapid maneuvers on the ground, and they're constantly feeding information back and forth.
That's a perfect analogy, yes. This structure allows for something the researchers call hierarchical convergence. Basically, the low-level module zips through multiple fast computation steps, and it reaches a kind of local equilibrium. Think of it as the tactical unit perfecting one small objective. Only when that local task is stable and sorted does the high-level module advance its own state, updating the master plan, if you will.
Ah, I see.
And this update then resets the low-level module, pushing it towards a new computational phase, a different local goal related to the next step in the big strategy. This design is really critical because it prevents something called premature convergence.
Premature convergence.
Yeah, it's a common issue where standard recurrent networks kind of get stuck in a rut or jump to a conclusion before fully exploring the details. HRM structure avoids that, allowing it to maintain high computational activity and effectively greater depth over many, many steps. It keeps thinking, refining.
That dual module architecture sounds really clever. But beyond that, how does HRM manage to be so computationally efficient and adaptive in its learning? It sounds like it could be incredibly demanding resource-wise, given all that interaction.
That's a great question, and it leads to another crucial innovation, its training method. It uses something called a one-step gradient approximation. Now, typical recurrent models rely on backpropagation through time, or BPTT. BPTT is notoriously memory hungry. Why? Because the memory needed scales linearly with time, with a number of steps.
Okay.
Think of it like having to reread an entire very long book from the beginning just to fix one typo on the first page. You need to keep the whole history in memory. HRM's method, however, has a constant memory footprint. It only needs to backpropagate errors through its most recent local activity. It's more like only needing to remember the last sentence you wrote to fix its grammar. Much more efficient and actually probably closer to how biological brains might handle credit assignment.
Wow, that's a big difference in efficiency.
Huge. And there's more. HRM also incorporates a deep supervision mechanism. This is inspired by how periodic brain waves, neural oscillations, seem to regulate learning windows in the brain. It provides frequent feedback during processing to the high-level module, like regular progress reports or checkpoints. This acts as a strong regularization technique, enhancing stability during training and helping it learn faster and more reliably.
And I read it could actually decide how long to think about a problem, adapting its computational effort. That sounds incredibly, well, human-like conserving mental energy.
Yes, and this touches on a really important question about efficiency and, what intelligence even means. HRM integrates adaptive computational time, or ACT. This draws direct inspiration from psychology's concept of System 1 and System 2 thinking.
Ah, the fast and slow thinking. Kahneman.
Exactly. System 1 is our automatic, fast, intuitive thinking, like recognizing a face instantly. System 2 is our deliberate, slow, effortful reasoning, like solving a tough math problem. HRM uses a type of reinforcement learning, specifically cue learning, to predict when it should halt its computation on a segment or continue processing. This means for easier tasks, it can stop early, saving significant computational resources with almost no hit to performance. But for tougher problems, it learns that it needs to think harder, allocating more steps, more resources. It optimizes its effort.
Okay, so the architecture is brain-inspired, the training is efficient, it adapts its effort. This all sounds incredibly promising, theoretically. But how does HRM actually perform on those real difficult reasoning problems, the ones that really push current AI to its limits?
The results are, frankly, quite remarkable. HRM achieves what the paper calls exceptional performance on tasks that are often considered intractable for even the most advanced LLMs. And here's the kicker. It does this using only about 1,000 training examples per task. No massive pre-training data set, and crucially, no chain of thought data fed to it. And get this, the model only has 27 million parameters.
27 million, compared to billions or trillions in LLM.
Exactly. It's tiny in comparison. It's like a highly skilled artisan solving complex problems that giant automated factories just can't handle, using vastly fewer resources.
Okay, give me some examples. Where did it shine?
Right. So take Sudoku Extreme Full. This version requires serious tree search, lots of backtracking. It's hard. HRM achieves near-perfect accuracy. State-of-the-art COP methods, even applied to much larger transformer models, they completely fail. 0% accuracy.
Zero. Wow.
0. Then there's optimal pathfinding in complex mazes 30 by 30 grids called maze hard. Again, HRM got near-perfect accuracy. COTI methods failed entirely. Couldn't find the optimal path. And maybe most impressively, on the abstraction and reasoning corpus, the ARC-AGI challenge. This is a key benchmark for AGI. It tests abstract reasoning, often visually. It stumps humans sometimes. HRM significantly outperformed leading COTI-based models like O3 Mini High and even Claude 3.7, despite those models being considerably larger and using much longer context windows.
Those performance figures are genuinely astounding, especially given the model's small size. Now, here's where it gets really interesting for me. Does HRM use just one single reasoning strategy? Like, is it always doing depth-first search? Or can it actually adapt its approach depending on the problem it's facing?
It absolutely adapts, and that's a massive step forward, right?
Yeah.
When the researchers visualized its intermediate computational steps, they saw it clearly using different approaches for different problems. For the maze task, for instance, it initially explores multiple potential paths, sort of branching out its options. Then it systematically prunes the inefficient ones and refines the solution, converging on the best path.
Okay, like exploring and narrowing down.
Exactly. For Sudoku, its behavior looks strikingly like a depth-first search. It explores possibilities down one path, hits a dead end, backtracks, tries another, just like a human might tackle a hard Sudoku.
No.
But for the ARC tasks, which often involve spotting abstract patterns and making transformations, it does something different again. It makes these incremental adjustments, iteratively improving the state of the board or grid until it reaches the solution. It's more like a hill-climbing optimization process.
Fascinating.
This ability to autonomously select and apply an effective strategy for each type of task is really key to its success. It's not stuck with just one way of thinking.
We started this by talking about brain inspiration. Does HRM actually become more brain-like internally after it's trained? Are there parallels you can actually observe, things that emerge from the learning process itself?
Absolutely. And this, I think, is one of the most profound findings. There's a key principle from neuroscience called the dimensionality hierarchy in the brain. What that means, basically, is that higher-order brain areas, the ones doing complex reasoning, abstract thought, they seem to operate in neural representation spaces that have higher dimensionality.
Higher dimensionality, meaning
Right.
more complex representations.
Kind of. Imagine thinking about a problem not just in simple terms, but with hundreds or thousands of interconnected facets or dimensions of information simultaneously. It allows for richer, more flexible representations. We can measure this using a metric called participation ratio, or PR. A higher PR indicates a richer, higher dimensional space for representing information.
Okay, so how does HRM measure up?
Well, after training HRM on Sudoku, they measured the PR of its internal states, and they found a striking parallel to the brain. The high-level module state operates in a substantially higher dimensional space. Its PR was around 89.95. The low-level module operated in a much lower dimensional space with a PR of about 30.22.
Wow, a clear hierarchy.
A very clear hierarchy. And what's truly astonishing is that this hierarchy is an emergent property of training. It doesn't exist in an untrained network with random weights. In an untrained network, both modules have low and basically identical PR values, no separation. This means HRM learns to organize its internal thought space hierarchically. Much like the brain seems to organize itself to handle different levels of abstraction, from concrete details up to grand concepts.
It's not just designed to be hierarchical in its structure. It organically develops this sophisticated, multi-layered internal organization through learning. That feels different, like it's learning how to think, not just what to think.
Precisely. And this learned hierarchical organization of dimensionality is thought to be fundamental for cognitive flexibility in biology. Interestingly, the ratio of the high-level PR to the low-level PR in HRM, about 2.98, closely matches measurements from the mouse cortex, which is around 2.25. This is also a significant departure from a phenomenon called neural collapse, which is often seen in standard deep networks.
Collapse?
Yeah, where during training, the learned features all tend to converge or collapse into a low-dimensional, less flexible subspace. It can hinder generalization. HRM seems to avoid this, maintaining this rich hierarchical structure. It suggests HRM isn't just memorizing, it's discovering and embodying a fundamental organizational principle for robust, adaptable reasoning. Something much closer, perhaps, to how nature does it.
This whole deep dive into the hierarchical reasoning model, it really feels like it reveals a potentially profound shift in how we might approach AI development. It strongly suggests that focusing on these brain-inspired architectures, on emergent properties like that dimensionality hierarchy, rather than maybe just scaling up existing models, that could unlock truly groundbreaking reasoning abilities.
I agree. HRM presents a really viable and demonstrably effective alternative to the chain of thought methods that are so dominant right now. By leveraging this hierarchical structure, multi-timescale processing, efficient training, it's advancing us towards a foundational framework that could be capable of Turing complete universal computation. That means, in theory, it can simulate any computation. It moves us beyond the inherent computational limits of standard transformers, opening doors to potentially more general forms of AI.
So what does this all mean for you, listening to this? This isn't just about AI solving Sudoku puzzles faster, right? It's about the potential for AI systems that can independently, efficiently, and flexibly reason through incredibly complex problems, adapting their thought process on the fly, much more like the human mind does. The implications for things like scientific discovery, engineering challenges, complex system analysis, even how we understand intelligence itself, they seem immense. And it leaves us with a thought. If an AI can learn to mimic the brain's multi-layered reasoning with such startling efficiency and with relatively little data, what fundamental principles of intelligence might we still be overlooking in our broader quest for truly general AI? And what new frontiers of problem solving, maybe even creativity, will this kind of architecture unlock next?